well, welcome to part 2 of the Understanding the Impacts and Risks of Building Envelope Upgrades. So today's webinar will be bringing in topics discussed in part 1 through case studies and lessons learned. My name is Jenna. I'm a Built Environment Initiatives Coordinator with the Community Energy Association, and I will be facilitating the webinar this morning with support from my colleagues Mariah and Terry. I'm going to give a quick introduction and then pass things along to our speaker this morning. Jeff Kirkpatrick with RDH Building Science will be taking things away from me in a couple of minutes here. So just the next slide there, please, Jeff.
Oh, that's me. Why isn't it working?
There we go. Perfect. Thank you. All right. So this morning I am joining from what is now known as Christova, a small community just outside of Nelson. And for thousands of years has been the traditional territories of the Sinixt Nation, the Silks Nation, and the Kootenay Nation. So just like to start this morning by expressing my deep respect and gratitude for their generations of stewardship in these waters, mountains, and forests. And as part of CEA's commitment to truth and reconciliation, I like to start these webinars with acknowledging some Indigenous leadership in the built environment space. So we'll start with this story here, and you can find more information about the details of the story just in the top corner of the screen there. So Sanak is part of the unceded territory of the Squamish Nation, whose history on this land stretches back to time immemorial. So originally a seasonal fishing village, it evolved into a permanent settlement in the 19th century. And in 1868, the federal government established Kitsilano Indian Reserve No. 6, a parcel of land of approximately 37 acres. Over the decades to come, it was further annexed until the Squamish residents were provided a small stipend and barged off the land. So after a protracted legal battle beginning in the late 1970s, the nation regained ownership of the 10.5 acres of the Kitsilano Reserve lands in 2003. So today is the next chapter for those lands, where development of Sanak has the potential to not only partially right this historical injustice, but also add significant new, much needed low carbon rental housing to the city. So the development of the Sanak lands aims not to only address this historical injustice, but also to provide much needed low carbon rental housing for the city. The project will honor the Squamish Nation's rich history while showcasing a path forward in sustainable and equitable urban development. So the development will create a highly sustainable mixed use project of primarily purpose-built rental housing of approximately 4 million square feet or 6,000 units. And Sanak will be one of Canada's first large-scale net zero operational carbon housing projects. So it's a distinct energy system developed in collaboration with Creative Energy, will harness excess heat from the nearby Metro Vancouver infrastructure to provide a carbon-free energy source. And the buildings will meet step 3 of the BC Energy Step Code and feature high efficient triple glazed windows to reduce thermal and noise transfer. Apartments will include energy efficiency appliance and fixtures to conserve water, while the development's design promotes alternative transportation options, minimizing reliance on automobiles. So in phase 2, the commercial building will incorporate 45,000 square feet of mass timber construction, a material with 50% lower embodied carbon than conventional concrete. And finally, sustainability features include green roofs, permeable paving, native landscaping, and systems for capturing and reusing rainwater for irrigation. So again, if you're interested in learning more, just visit the links at the top of the screen there. All right, and just the next slide there, please, Jeff. Just a quick introduction to the Community Energy Association. Who are we? If this is your first time joining, CEA is a registered charity and nonprofit. We're committed to accelerating bold action by local governments and Indigenous communities related to climate and energy. And we are the only nonprofit in BC focused exclusively on supporting local government and Indigenous communities on these projects. So what does that have to do with building better? Well, CEA's work recognizes that the built environment is a main source of community-based greenhouse gas emissions, and that action in these sectors can not only result in significant GHG emission reduction, but can lead to enhanced community resilience and energy security while increasing the comfort, health, and safety of our homes. So CEA, we've been involved in building industry education and capacity building for almost a decade. And on the next slide, I'll quickly introduce a few of our current projects. Thank you. So building a legacy, Kootenay Clean Energy Transition and Retrofit Assist are examples of these projects. Building a Legacy North is a collaboration of CEA and the Canadian Home Builders Association of Northern BC, and it focuses on supports for the building industry and local governments in the cold climates of Northern BC. The Kootenay Clean Energy Transition, a KSET, assists communities in preparing for a more energy efficient and healthy future in the Kootenay and boundary regions. And Retrofit Assist offers a comprehensive concierge service to guide homeowners through the process of completing home energy retrofit projects with the optional financing available. So if you are a retrofit contractor working in Roslyn, East Kootenay, Kamloops, Whistler, or Squamish, this is a program you may be interested in learning more about. And I will pop some links in the chat for you along within the follow-up email. But we do onboard retrofit assist contractors in these regions who then support homeowners in the program and completing their home energy upgrades. All right, so today's webinar is in thanks to the generous support of the organizations listed just at the bottom of that last slide there. And then just one final plug before I pass things over. If you're involved in retrofits, I'd just like to introduce the Home Performance Contractor Network, or HPCN. So if your clients are looking to access provincial and utility rebates for heat pump installations, window and door retrofits, or installation upgrades, this is the network for you to join. So feel free to reach out to me if you have any questions about this network, or just contact the info@ email address on the slide there. All right, so just a couple housekeeping items here. CEA, we're dedicated to offering educational opportunities to all, no matter their current knowledge or experience level, and we prioritize creating a safe and welcoming environment for attendees to engage and participate. So with that said, please ask your questions. The format of today's webinar will be a little bit different. Jeff will provide a brief overview of part 1 and building science fundamentals before moving on to case studies. And we're going to pause after each case study to hear from you folks if you have any questions. So feel free to pop your questions in the chat as we go along. I'll be keeping an eye on them, and then I can ask Jeff on your behalf, or feel free to raise your virtual hand and ask Jeff directly when the time comes. We'll be sharing out copies of the presentation, slides, and recording. And then for those of you collecting CPD points, we'll be sharing out confirmation of attendance email for everyone who's stayed on for the full duration of the webinar. Okay, and with that, it is my absolute pleasure to introduce Jeff Kirkpatrick with RDH Building Science. Jeff is a part-time studies instructor with BCIT Zero Energy Emissions Building Learning Center and is a registered energy advisor actively working in the Central Kootenay and Kootenay boundary regions. So we're incredibly lucky to have Jeff here with us today, imparting some of his wisdom and knowledge achieved through 30 years of experience in residential and commercial construction. And with that, Jeff, I'll pass things along to you.
Thank you so much, Jenna, and welcome everybody for joining us today. I appreciate taking the time. We'll jump right in and make sure we have lots of time for interaction and questions. RDH will also like to acknowledge the traditional territories of the Sinixt, Silex, and Ktunaxa peoples. A brief disclaimer, legal jargon required by the powers to be. Today's agenda. Part 1 refresh, we'll just backtrack a little bit and touch on building science principle foundations. Building as a system, run through a few case studies to highlight some of the considerations in house as a system, some safety items, and then open for discussion. And I hope to encourage lots of questions while we have the opportunity. We also have James Bourget here with us today as a resource, and we're in the lab in the Meadow Creek mock-up lab. Some definitions: retrofitting from Natural Resources Canada, energy efficiency retrofit, upgrade energy consuming systems, TUI. Retrofit definition is an act of adding a component or accessory to something that did not have it when manufactured or constructed. So minor retrofit would refer to air sealing and insulation, or upgrade lighting, or low flush toilets, small low hanging fruits that can be achieved by whether at a contractor or a homeowner. A major retrofit definition would be replacing windows and doors, updating mechanical, heat pump, low flow faucets, install sub-metering, top up in attics, easy, relatively easy accessible components. And then a deep retrofit is an extensive overhaul of building systems, saving 60+% in energy cost, generally requires the exterior upgrades in regards to the air barrier as well as insulation values. So air sealing and insulation upgrade retrofits. The process starts with assessing the options for improving the envelope. It's critical from the house as a system standpoint to address the holistic nature of all of the systems of the building. And that's really what we're trying to stress here repeatedly in the previous presentations and today and beyond. Performing air tightness testing and air sealing is usually the best place to start. This generally involves getting a pre-evaluation of the existing home so that we can understand the metrics. We're trying to ascertain the full context of the environmental separation, windows, doors, content of the walls, and the air change metrics of the building so that we understand what are the performance bases to developing what is the heating and cooling loads required for the building, what is the indoor air quality context. Window replacement should also be considered, especially if you have aging windows. And adding insulation is usually the most work. So adding insulation to your exterior walls are definitely a difficult consideration, whether I'm addressing the existing wall and adding insulation to the existing wall, or whether or not I'm adding exterior insulation on top of the exterior. Attic insulation requires special considerations in regards to the opportunity for air sealing. At the time that you're in the attic doing the additional work, there are some extra steps that can dramatically improve the performance. Insulation top-up priorities. An insulation top-up for smaller budgets where interior-exterior retrofits are not possible. Generally, the attic insulation, an easy place to get in and get some dramatic improvements with the air exfiltration, as well as the resistance to heat flow through the attic space. That is where all of our heat is going as we're conditioning a space and stratifying that buoyant air up through the envelope. Is sitting against our attic plane. Crawl space insulation, and where we're generally pulling the cold air and fighting the conditioning as a result of a poorly addressed crawl space. So crawl space insulation is a great place to start. And always air seal first. So all insulation top-ups require the consideration for air sealing. If we can reduce those two metrics, we get the dramatic improvement in the performance values. And then the other options are an exterior retrofit when we want significant energy improvement, or an interior retrofit when significant energy improvement is desired, but the exterior retrofit work is not feasible, i.e., heritage homes, or maybe a complicated brick assembly, or in a lot of cases, it's complex exteriors with lots of elevation changes, bay windows and dormers, and it gets quite costly. The more complex the envelope is, the more complex it is to create those continuity in the critical barriers as what I lovingly refer to as the sweater and windbreaker effect. Just like everything in nature, when we get up in the morning and we go to experience a cold day outside, I ensure that I have a wind resistant layer and a good thermal layer in order to mitigate the exterior environmental conditions. And our organic buildings are exactly the same in principle. So why the enclosure first? Air tightness, thermal, and mechanical. So our existing homes are especially a pre-70s. So we look at the era up to the 40s before we had building code. Buildings were generally uninsulated or insulated with things like horsehair or wood shavings. And so we've had quite leaky envelopes. 60s and 70s, we started to implement draft proofing, but not air barriers or vapor barriers specifically. 70s, 80s, we start realizing that we needed more protections in the wall assembly. So our existing homes are quite leaky. So it requires large mechanical systems to meet that need as a result of the air loss or low resistance to heat flow. Windows, doors, penetrations, base of wall, eaves, soffits, all areas for air leakage, requiring even more mechanicals to meet the climatic changes within our environment, whether that's through climate change or through the impact of the cost of conditioning, adding our energy costs. If I take away some of the air leakage within the envelope, basic air sealing attempts, add some windows and doors, and improve the control layers in the wall assembly, I can reduce my mechanical needs. add a little bit more insulation, and I can reduce my mechanical needs further. So this relates to the two dials I have to effectively adjust the performance value of a building. I have my TEDI, my thermal energy demand intensity, a function of my air tightness and my thermal insulation values, or resistance to heat flow within the wall assembly, or my mechanical, my MUI, my mechanical energy usage intensity. So if I can turn up my air tightness, which means reduce my air tightness and improve the insulation values of my walls, and that includes windows and doors as part of your air tightness and thermal metrics for that wall assembly, then I can reduce my mechanical needs. If I can't turn up my TEDI dial, it means I have to turn up my mechanical dial to compensate. Those are really the two functions. And obviously the envelope first approach refers to turning up that TEDI dial wherever possible so that I can lower the conditioning needs and cost. The old building enclosure, as I said, separates inside from outside, keeps some warm air in and keeps some cold air out. Typical low tightness and air tightness and thermal performance, but gave us good longevity in the sense that the energy loss was a drying mechanism for the walls. So it kept that fine balance between wetting and drying. And the cost of energy wasn't as much of a consideration as it is today and into our future. So we continued to pump those old dinosaur furnaces that came on every 30 minutes and pumped the house full of hot air, but 15 minutes later, it was right back on again to compensate for the losses. Pretty good building enclosure separates the inside from the outside and then keeps the warm air in and keeps the cold air out. Varying levels of performance depending on how well it is designed and constructed. So that's improving the thermal resistance and reducing the air change rate of the building will get me to that pretty good standard and beyond. The critical environmental loads that are applied to our existing buildings are the exterior environmental conditions and the interior environmental conditions made up of our 5 critical barriers. Starting on the outside of the wall is our water shedding surface, meant to keep 90% of the water out of our wall assemblies. Second line is our water resistive barrier, which is the final plane of protection for our walls, meant to stop any incidental moisture that comes through the cladding assembly or water shedding surface. Our thermal insulation, which is our resistance to heat flow within the wall assembly. The vapor barrier or vapor diffusion within the wall assembly, in this case, the poly behind the drywall. It can be vapor barrier paints on the drywall. It could be multiple coats of latex paint on the drywall. It's an impermeable barrier meant to retard any vapor diffusion migrating through that linear path into the wall system. And our air barrier, a function of continuity through the envelope, in this case, poly by default, is it being the interior plane of protection. It can also be your exterior plane of protection, utilizing the water resistive barrier, creating a continuity through from the footings to your roof line, across the ceiling plane, and back down your walls to the footings again, wrapping that exterior, which is in effect your windbreaker on the building, adding those insulation layers to increase the resistance of heat flow to the wall. So those are our 5 critical barriers to make up any wall, roof, or foundation system. We look at building as a system, or house as a system, as a 3-legged stool, requires 3 critical components to that enclosure conditioning. So my ventilation needs, my heating and cooling needs, and then the enclosure environmental separator requirements. So any one of those components out of balance makes it a very uncomfortable stool to sit on. And the critical balance required between those components. And that's why we refer to house as a system as being a very important component of our assessing and improving the performance of our existing buildings. And we'll touch on the case studies. We'll highlight why we believe this is so important. So again, the enclosure, which is our environmental separation, the ventilation system, which is our indoor air quality and conditioning, and our heating and cooling systems, which are our indoor air comfort within the space. So for our first case study, interesting scenario, the relatively new home with double glazed windows is getting an upgrade on the windows as a result of excessive condensation from a new owner taking possession of a building. Did some mechanical upgrades in that process of taking ownership of the building and changing the occupant loads. And then notice that during the heating season that they were getting a lot of condensation on the windows throughout the home pretty consistently. They called a window contractor, assuming that it was a window deficiency. Window contractor sold them on replacement of all existing windows with, I believe, triple glazed windows. And the condensation problem continued. So further investigation determined that when they swapped out the existing forced air furnace system and went to a condensing system, there was a disconnected return in the basement area, but primarily due to changing the interior climatic conditions. So a number of factors, one being the occupant load. So they increased the occupant load through additional, we have more people occupying the space. Respiratory is a largest contributor to relative humidity in the space. And then also changing the mechanical as a closed loop system, so it's not processing the interior humidity controls in the same way that it was before. So you combine all of those elements together, and hypothetically they would have a 20-degree interior temperature during the heating season. Their humidity levels may be in excess of 60-70%, so quite high humidity levels. The dew point of that air can be anywhere, 10 to 15 degrees. So the window surfaces are double glazed in winter conditions can hit the dew point and cause excessive condensation within the space. So interesting that, a small changes in the envelope, and then in this case it's a newer home post 2000 with a higher ACH rating and higher insulation value. So the very delicate balance of changing mechanical systems and not ensuring that I've addressed the indoor air quality or monitor or even had any indication of what that indoor air quality metric was. In this case, called the contractor, got fed a line. The contractor a window contractor wants to sell windows, so they sold them on the windows, which didn't solve the problem. So unfortunately, having that holistic approach and ensuring that I have a thorough evaluation of the building performance metrics and understanding where is my money best spent on making improvements. So for reference, new homes must have continuous ventilation. All homes must have dedicated mechanical ventilation systems ducted to each living space, and it must run continuously during the heated season. Example, when your windows are closed, and must include a fresh air intake. So dramatic changes to our indoor environments during the heating seasons when we close all our windows and doors. If we do not have dedicated air intake or exfiltration, then where is that air coming from? It's coming through our walls. Example 2, or case study 2, an insulated crawl space with no vapor control. So fantastic that they've gone and insulated this crawl space area and trying to convert it from a open vented crawl space to a closed crawl space. But again, if I don't follow the bouncing ball all the way across the screen and complete all of the critical barriers as referenced earlier in the show, then I'm at a high risk. So I wanted to include a couple of photos that I took just this week in regards to frosting at the headers. So in this case, if I was to pull down some of that insulation, because I'm missing a vapor barrier or an air barrier in this case, the interior conditions are able to migrate through or past the insulation layers to the exterior surfaces. And then we'll show you in some thermal images later what that sheathing plane temperature looks like. So in this case, with this basement crawl space area in those headers, if my exterior temperature is say -10, it means my sheathing layer can be anywhere, -6 to -8, which is a condensing surface for those conditions. Without those additional control layers, air and vapor, I'm not able to mitigate the moisture meeting behind the insulation on cold surfaces. So in this case, if I was to remove that insulation, I potentially am going to see frosting at the outer rim band, or the connection between the joisting and the exterior wall. And I can attest to this because I see it. So it's not, it sounds like a theoretical value that I'm making things up, but these are real conditions that are happening in our homes in our existing stock assemblies with poor air barrier components or vapor diffusion components within that wall assembly. So critical that if I'm going to condition a basement, I need to ensure that all critical barriers have been addressed and that I have the continuity through that system. Is there any questions so far in these two case studies that we've attempted?
We
I don't know.
had a comment about the first case study, and folks, if you have questions, go ahead and pop them in the chat. Maybe indicate the case study number that you're referring to there. But just on the first case study, Calvin just commented that he's found a lack of return air in the home, specifically the basement compared to the upstairs, helps immensely when changing or upgrading heating.
Sorry, can you say that one more time, Jenna?
So he's just saying that he's found the lack of return air in the home, specifically the basement compared to the upstairs, helps immensely when changing or upgrading heating. So just a comment there on the case study.
Interesting. Yeah. So a lack of dedicated fresh air. Mm-hmm. I'm not too sure whether, I mean, the critical of, oh, I see. I found the lack of return air in the home, but basement.
Yeah. Sorry, Jeff. I was just, when I've done some retrofits, there's not enough return air in the basement, I find. So when you add that extra little bit of return air in the house, and it's a little bit tricky when the house is finished already, of course. So it does balance out from upstairs to downstairs by 3 to 4 degrees. Actually, when you add the return air in the basement, a lot of times they didn't put a lot of return air in the basement. That's what I found, especially up here in the north. So.
Yeah, that makes total sense. And it does relate directly to the consideration with that first case study. You're absolutely right in creating that balanced.
Yeah. And then on the second case study, it's interesting. I'm working up in a lot of the remote reserves, and we're having an incredible challenge with all the mold that's in the houses. And just with your description here, of course, we go in usually the spring or summer, so we don't see the frost. And so this will be something I'll be definitely looking at, because I'm going to assume that this is what's happening into the winter time. We get all the moisture and change in there. And by the time the spring comes or the summer comes, then that moisture is just turning into mold.
You're absolutely right. And it is a consideration. And you would, if you were to go during those during those winter conditions and did some exploratory work, you would see exactly as I'm describing that frosting on the perimeters. And we have some very unique situations with the northern remote communities and their present existing stock, and putting buildings that we would put on the coast in the northern remote compliant environments is not conducive to, they are completely different environments and require different considerations in regards to the air sealing metrics, insulation values. Again, the stuffed wall principle requires, it relies on that heat loss mechanism as part of the drying potential for the building. And so we've existed in that fine balance for quite some time, but it's not conducive to making changes or improving and reducing the insulation or improving the conditioning value. I mean, ultimately, all existing buildings or new buildings within the northern remote environments require exterior insulation. It's the only way to mitigate those interior dew points, those climatic conditions having that effect where we are getting the icing. You want to get rid of the icing or the condensing planes within the building, add the insulation layers and move the condensing plane out of the wall assembly. It's pretty good science. It's, everything in nature represents, you and I got up this morning, put a control layers on the outside. It's a critical function for us to move forward. As far as wintertime heating, it's a matter, I'm increasing that resistance to heat flow, but I'm dramatically improving the resiliency of that building because I'm moving those risk mitigations outside the wall assembly to where it's manageable and it doesn't have an effect on my critical structure. Even in summertime, it has a dramatic effect on our cooling requirements. So I'm doing a deep energy retrofit on my home this year, primarily because I want to increase the value of the property. I want to use it as leveraging, but more so, and I want to increase the life cost factor so that I can ensure that I have good value in that home long into the future. But I primarily want to eliminate cooling. I I get, a dramatic overheating process late in the day on the existing assembly. And so adding that exterior insulation will thermally break the cladding assembly and dramatically, reduce or even eliminate my cooling needs in the winter or in the summertime. It's going to have obviously a dramatic effect on my heating conditioning required, but that's more so a function of my air tightness metrics for improving the heating conditioning of that space. So putting the sweater and windbreaker on any existing stock home gets us to that 60+% improvement in indoor air quality and conditioning. So, the real function is that, and then you can see in this slide on the right hand side there, the vapor is condensing on that sheathing plane. So again, like I said, when we get into the thermal images I've provided, we'll actually see that condition of my sheathing plane. If I've got that -10 outside, my sheathing plane is only a couple of degrees colder or warmer than my exterior conditions in an uninsulated exterior, no exterior insulation. There's very little protection course for that sheathing plane, and my dew point is within the wall assembly. So especially with the northern remote communities, one of the biggest issues that we have up there is the rhetoric around the HRVs that have been provided in a lot of these homes over the last 20 years. They're not being used because, one, they think that it's something that's running all the time, it's going to cost them more money, and it's not. And then when it is functioning, they haven't found that balance between their existing conditioning equipment, the ventilation rates required, the stuffed wall principle that they're existing in up there, which is fraught with risk. And then the fact that the HRVs aren't managing those interior climatic conditions effectively. Generally, they get shut off. In a lot of cases I've seen, they didn't even get turned on. And so these buildings we're right back to square one. There's, it's a major, consideration now improving that. I'm actually involved in SAS Power, where we're providing a new build process for these northern remote communities and ensuring that we don't continue with business as usual on the stuffed wall principle, that we give builders the option to move towards exterior insulated assemblies so that we can improve the life expectancy of the building, reduce risk within the envelope, and create a much healthier indoor environment.
Yeah, one of the problems, what I've noticed actually, if I find out residents up in, say, one of the reserves we're working on, if it's a concrete one, that's usually pretty good. But if it's a wood basement, this is where we find I've never seen mold like this ever before. There's more than 101 Dalmatians in the basement, and it's the scariest thing you've ever seen. And I wonder if it's from the wood basement compared to the concrete.
It's the difference in thermal resistance values from the concrete to the wood. The air change metric. So obviously the concrete itself is an impermeable, so it would be considered an air barrier. But on a wood foundation, I've got all kinds of penetration, butt joints, intersections between components. So it's obviously it's a different metric in order to maintain that conditioned space. And any good wood foundation would serve with exterior insulation, just like our walls. So it's the same principle. A roof, wall, and foundation require those 5 critical barriers in the same, and it's just physics. It's the function of heat flow through the wall assembly. So it's just good physics.
Okay, thank you.
Yeah, no problem.
Great. Thanks, Calvin. We do have another couple questions in the chat. This next question is just a general question about air sealing and insulation retrofits. So just acknowledging that every house is different, but because there's no professional licensing of air sealing and insulation contractors, how can a homeowner ensure that the correct retrofitting technique is selected and implemented properly?
Well, and again, as I touched on earlier, there's the age relationship to our buildings. So, 2000 to present is going to give us a bit, we're going to have all of those control mechanisms, and it might be a function of they were installed well or installed poorly, but we have all 5 critical barriers in a 2000s to current existing home. Throughout the 80s and 90s, the critical barriers were there, but they were even, less focus on the air barrier, more focus on the vapor, because we knew that there was an issue with vapor within wall assemblies. And then if we move beyond 70s homes, where it's craft batt is our draft proofing and vapor diffusion layers within an existing home, And then pre-60s all the way on, it's just a mixed bag, really. At that point, you know, before 1940s, there was literally nothing, or wood fill, you know, wood fill shavings, or horsehair, or any number of components within the wall assemblies. So yes, your existing stock home and the where it falls into that age relationship is going to have unique considerations. Really, what I want to highlight by that is that as you move down throughout the ages, there's less control mechanisms to work with. So obviously, if, you know, hypothetically, if I was to take a 1950s house, my most consistent control layer in that building is the interior finishes. So in essence, we refer to it as the airtight drywall approach, where I'm going to use that drywall plane, or lath and plaster, whatever that continuity interior finish plane is, will be my air and vapor diffusion layer. So if I apply, you know, multiple layers of latex paint or a vapor barrier paint to that assembly, reduce its permeability rate, and then seal windows, doors, penetrations, seal the drywall to the floors, to the ceilings, and look at that continuity. So the critical function is that air sealing is a function of continuity. I'm going to look at that envelope, whether it's inside, exterior, airtight drywall approach. I'm looking for consistency in my air sealing. Vapor diffusion is a function of coverage. As long as I cover 90% of the area, I have a 90% effective vapor diffusion layer. And it's the pressure differential between exterior and exterior that is causing that air leakage, right? So the critical function, and yes, there is no professional organization. There is an extensive amount of experience, you know, write-ups, documentation, conversations around the air tightness, what components, what materials can be used for different assemblies. So I would refer, there'll be some links at the end of the presentation. There's a wealth of resource out there through BC Housing, through National Resources Canada. Keeping the Heat by National Resources Canada will talk, you know, quite extensively about different options, whether I'm air sealing and insulating an attic to a foundation to a crawl space. There's pictures, diagrams, and explanations of the, you know, of the building science fundamentals and what you're trying to achieve. So no matter what era of building that you currently occupy, there are opportunities for dramatic improvements, but it requires that holistic approach where we're taking into account what is the existing tested capabilities of the building, what do I want to achieve, and what are the metrics to get there. Requires some careful consideration, and it requires, you know, being a good consumer, getting as much knowledge as I can, relying on the resources that for guidance, your energy advisor, any one of these publications, any one of the consulting agencies. You know, there is a wealth of resource, and it seems quite daunting. I monitor a lot of forums. I understand, as a an experienced homeowner, the difficulty in determining what is the best course of action. But I will say that there is a numerous resources. We'll be providing some links at the end. And to just catch the rest of your question here, your original home was built in 1966, and you want to air seal and insulate the rim joist cavities better. But it looks like the current basement wall is designed with an intentional air gap at the top of the finished wall to allow moisture. That's, yeah, that is a unique system. And you know, when we look at the existing building with the lack of critical barriers, in the end, in order to meet the conditioning or the consumption value in reduction, I want to apply that 5 critical barrier mentality. So I want to look at that wall assembly, you know, in that basement in application, and I want to ensure that I have continuity. The air gap that you're referring to, and if it's what I'm picturing, obviously without any photos or anything to go by, presents a very unique but, you know, very common risk to that assembly, and it's referred to as convective looping, where warm, moist air can enter that cavity, make contact with the cold surfaces, in this case the foundation, cool and drop the moisture out of the air. As that falls, it draws more new air in at the top, and you get a convective looping cycle. And this is what we refer to as the musty basement smell, is generally because of a convective looping process, where I'm getting that sweating and then drying and sweating and constant feed process because of the thermal properties of the wall cavity and the ability to pull air in and cool the air and continue that process. So we don't want to have an air gap, as I was describing in this in the slide on the screen in regards to that continuity. I'm not going to get a convective looping process here because I'm missing the critical barriers. But if I was to complete the critical barriers to make this assembly complete, I would ensure that I've created an effective air barrier from that flooring, from the plywood, from the floor above, because I'm trying to connect those thermal planes from my wall above to my header to my foundation. I want a consistent value vertically through the wall, through those floor bands and in the wall assemblies. So I need a consistent insulation value, but I also need to be able to kind of connect that air and vapor diffusion layer. And in this case, it would be potentially poly by default on the inside. I would need to castle through my joisting, or I can use any number of rigid insulation products. If you're going to spray foam headers, there are some additional considerations that not all spray foam applicators are created equal. It's critical that you take some efforts to air seal the cavity before spray foam. Spray foam does not maintain its intimacy to the building components over time. It could due to interstory drift, racking of the building, the temporal impact between winter and summer on the organic nature of the building. The wood components are always moving within our building assemblies. If I have a rigid product like spray foam, it's not going to stay effectively adhered to those components. So pre-striping with a sealant or tapes to reinforce the ability for that spray foam insulation to be able to interact with the wood framing around it. Again, we'll get into that a little bit further along. I've got some slides to illustrate that. But that critical, I would not maintain the air gap, the intentional air gap in that assembly. I would create the critical barriers as they're designed to function based on the laws of physics. So we'll move forward.
Yep, sounds good.
Jen is I'll run out of time and I'll be in trouble by Jen as usual. New blown-in cellulose made it hard for walls to dry out. And another interesting case scenario where an existing old farmhouse with no insulation at the time of conception, insulation was later added. So the existing wall assembly functioned because of the internal heat gains were driven out through the wall assembly. So in this case, we would have excessive wetting and frosting in those walls in the wintertime, but we have excessive drying mechanisms during the off seasons. So that building and resiliency of the wood. So we, be 100-year-old cedar wood. I had a 1901 in New Westminster. That wood was absolutely AAA grade by today's standards. So the resiliency and the antimicrobial nature of that old cedar and the ability for the building to provide that drying mechanism on its own, as well as the exterior environmental conditions creating drying mechanisms within the wall. That building existed for 100 years. They added blown-in insulation from the inside to the walls, which reduced the heat flow through the wall from the interior, which increased the condensing potential within the wall assembly, to the point where now the walls were wet, musty all the time. They weren't drying effectively, and it was actually causing bulging at the base of the wall because that extra loading on that cladding assembly, the moisture content, the density of the blown-in, the cellulose insulation was packing down at the bottom and forcing the bottom of the walls out. This required a complete envelope upgrade, unfortunately. So then the best R value improvements. We'll just run through a scenario of a 1960 rancher, pretty common built home in our environments. So my walls are R12 at about 1,000 square foot of wall surface. My attic is an R20, batt or loose fill insulation at about 1,200 square feet. My floor above, whether on grade or above crawl space, is an R20 at 1,200 square feet. And old windows, so maybe aluminum single pane, and R1 is generous in this case, but accounts to 125 square feet of that combined envelope area. That's 3% of the envelope represents 40% of the heat loss in that existing building. If I were to do an energy model on that building, the windows being the weakest link. The average weighted R value or UA value, would be at 10.8 for that wall assembly. So Like you say, you might have an R12 bat in that wall, but if I add up the window to wall ratio, the effective R value of all of the components of that wall assembly, I get an UA value, or an area weighted value, of 10.8. If I was to upgrade the attic insulation and add 9 inches of new attic insulation, I get to a value of R50. I've made a 12% improvement from R10 to R12. And that, again, is my area weighted average of the entire envelope of the environmental separation barriers. If I was to add new energy standard windows at R4, accounting for that 125 square feet of that envelope, I would have a 40% improvement from 10.8 to R15 for that overall assembly. So if I was to just add 6 inches of attic insulation and new windows, I gain a 60% improvement on the resistance to heat flow. So it's not a 60% improvement in my cost to condition the home. It's a 60% improvement in the overall area weighted average R value at 17.1. So dramatic improvement in that. And this is just sort of to highlight the importance of what is achievable today to get me some pretty big gains in improving that environment in this process, because I would be putting in new windows. I would ensure that that new window installation meets CSA A440, 419, that there is a potential that if I was to come back and take that upgrade further in the future, if it was a stretch goal, and as an energy advisor, one of the components I try to help people understand is where would I want to be as the best case scenario, and what are my steps to potentially get there. I may just be doing a version 1 at this point, attic top up in windows, but I'm looking at eventually I'd like to do the exterior envelope and air barrier components so that I get those bigger gains in the future. So this to me is a very a powerful set of slides to illustrate that we can make some pretty dramatic improvements right now with the existing rebate programs in place. This is a good scenario for an existing building.
Hey, Jeff, just a quick question there. If folks wanted, are there resources if folks wanted to do a similar kind of look at a building that they're looking to upgrade, and they want to know where they would have what would have the highest impact?
It would be the first step is an assessment. So you would need an energy advisor or consultant to do an energy audit on the building to find out what its current capacities are. And in that process, as an energy advisor, my main focus is to look at the environmental separation, from all 6 sides of the box, and ascertain what is my resistance to heat flow capabilities, my air exchange rate through those wall assemblies. What is the current capacity for heating and cooling? And then where would make the most sense to. So obviously, as from a building science standpoint, as an energy advisor, I always look at where would I want to be at the best case scenario? And then what are those steps to achieve it, and potentially doing a phased plan because of the cost prohibitive nature or accessibility to contractors or any number of the component, considerations. I potentially may have to do a staged plan. So your energy advisor can help you walk through, or any one of the consulting firms can help you walk through what are, if I was to do A, B, and C, or if I was to do it in B and C and then come back to A. Every home is unique and requires that evaluation and then the considerations. And like I say, we'll provide some links to some documentation that will help you understand the functional nature of your existing building.
Great, thank you.
Any more questions? No.
None directly about the case studies. I'll save those that aren't related to case studies till the end. But folks, feel free to pop your questions in the chat as we go along. Okay, so these 3 slides are actually my house at a -16 exterior temperature. So the ambient air temperature outside the home at about 7 o'clock at night was -16. So these thermal images and the temperature variances that you see on the screen and I've got a fairly fat wall. I've got 2x8 walls with EPS insulation. So they're fairly decent as far as a resistance to heat flow value. But you can see that and I heat primarily with wood, so that's why it's really quite warm on the inside. But this is my heat loss metrics, the conduction and convection from the interior conditions. So I'm warming my drywall surfaces connected to my studs. My studs are connected to outside.
I have some area for exfiltration through that assembly, and it's keeping my sheathing plane really quite warm in consideration. So interior conditions are maybe 22 degrees. The exterior is 16. The temperature is on the surface of some wood, vertical wood siding, but you can actually see the glow of the plywood behind that vertical wood siding. So what it is 5/4 decking. So there'll be two pieces with a cap piece over top. So there's actually a voids, 4-inch void space between each bit of vertical wood strapping, and you can clearly see that in these thermal images. So that's, we're not getting the temperature range. We're getting the temperature range of the surface of my exterior wall. So at a -16 exterior ambient temperature, the surface of my walls are -9 because of that heat loss, that conductive heat loss through the envelope. And as I move on the far right, as I move up to the headers, which are a solid component laying on the flat in contact with interior and exterior conditions and transmitting that heat energy through at the top plates, you can see it's quite warmer. It's 3 degrees warmer. And then there's in the far left is a penetration in the upstairs wall where I'm getting minus, it's really quite warm in that zone as well. And then obviously my windows is a radiative loss or glowing, glowing on fire. So these are some of the existing cases in Roslyn. So as I referred to earlier about convective looping, we can see in the far left and the far right photos, those are channels where in this case, this building received exterior air barrier and insulation upgrades, but didn't make the critical connections on the air barrier components. So they stopped at the top of the walls, they stopped at the footing, new windows and doors, and 2 inches of exterior insulation. The thermal camera on the inside shows that the attic insulation wasn't brought all the way to the top plate. So if we look in the far right image, you can see at the ceiling plane, there's 2 bays, 2 channels where there's little to no insulation. There's areas within the existing walls that were never opened up. And so there were areas where there was no insulation due to the age and the renovation history of the home. There was opportunities for cavities that had little to no insulation. You have penetrations through your top plates, sill plates, through your studs. Air is able to move within those wall cavities at will. So we can see, in the center photo is a close-up of that ceiling transition. That's that could even be moisture at this point, accumulating in the attic space, without doing more investigation. It's down at the eaves. That's a critical area requiring insulation intervention to cover your top plates. When I add heat to a space, I'm subject to surface temperatures, not just the ambient air temperatures. I use the example that if I was to go away for the weekend and turn the furnace down, come back and turn the furnace back up, it's an hour or more before I'm comfortable in that space. And that's because the energy being applied to the space is being absorbed by all the components, including my exterior walls, before that heat energy is radiated back to me in the space and I'm comfortable. So I always have a conductive by default loss of my conditioning. I have a convective loss through any air exfiltration points, and I have a radiative loss through all my windows or exposed components. Another view of, in this case, a scenario of in our winter conditions, we get a truss uplift, which creates a bit of a crack potentially at the wall to ceiling transition, and this is air leakage in the wintertime conditions, drawing air through those cracks being formed. On the far left is our log homes, which you really don't want to go and look at your log home with the thermal camera because it's quite depressing. But there are, again, mitigation materials. The log home industry itself provides interior chinking components. There are ways to mitigate your leaky air log building. And then in this case, windows and doors that have been retrofitted and not tied into the critical barriers. So this is house as a system. This is, best practices for installation of these components within penetrations. You can see the doors on the left, all kinds of air leakage at the header. There's no continuity between the wall and the window, or in this case, the door openings. The center photo shows the door has been spray foamed into the opening and is leaking profusely. And then brand new installed window, same idea, spray foamed into the opening will not stand up to air exfiltration or infiltration around the windows. And you can see that your brand new windows are leaking. Or spray foam adhesives, as I touched on earlier. Critical step to ensuring that I get continuity at the spray foam into installation at the headers is creating a flexible transition in all of my inside corners. If I have my rim joist on the outside, my joist run coming in, my sheathing plane on the top, I've got a three-dimensional interior corner. Highly unlikely that the spray foam insulation is going to bond to all three components equally. It doesn't bond well to that inside 90 transition. So if I run a bead of sealant through all of those areas prior to spray foaming, I can dramatically improve the actual air barrier continuity through those spray foam headers. So you can see in the on the right, so even after spray foam has been applied and has been sold as an air barrier or vapor barrier component, it doesn't meet the air barrier requirements in reality. So again, some more photos showing the excessive amount of air leakage even after those components are spray foamed. And if you really look closely at the left photo, you can see the inconsistency in the application. So the applicator didn't quite, focus on the critical areas, which is the bond to the wood components around the three sides. But if we look at the transition between the footing and the rim joist area itself, he's actually left gaps there as well. So that's one of the critical areas for air infiltration. When we're heating the space and all that air is stratifying up through the assembly, we're pulling cold air in for new air in from somewhere, and it's generally the headers in the basement. And a couple more examples of a lack of continuity. New windows installed, but no connection to the critical barriers. So in this case, air, vapor, and thermal. So both examples are quite bad as far as what that looks like as not making contact with the critical barriers. In the case of our existing stock homes where we have a poly by default as vapor diffusion, it's generally was meant to be an air barrier at the same time, or we have to assume it is. So when I install windows to a CSA A440 419 metrics, then I am required to make contact with those critical barriers, whether they're continuity or not. That's not for me to decide. If I see poly around a window opening, I am required to make sure that I make contact with, I'm not to make buildings worse, I'm to make them better. And this is an ongoing theme all year long, is windows are being installed in the openings, but not connected to anything, which reduces the thermal capability of the window or the air infiltration, exfiltration metrics of the window. And a couple more examples of that is the one on the left, that we have no contact with the thermal barriers. There is no air barrier installed. A bit of insulation stuffed in around the opening. As I was standing there doing the assessment on this window, the window was leaking profusely from the head. It doesn't show in the photo, but I was trying to illustrate that they didn't, one of the critical barriers was missing. So I went, poke my head outside, have a look. There's no head flashing above the window. Right. And then another condition, microbial growth in attics with new insulation, excessive moisture leaking into the attic space. As I said numerous times now, that heat is stratifying and sitting against the ceiling plane. Any penetrations, all of the light fixtures and fans and mounts within the ceiling plane are a high potential leakage area. And when that warm, moist air enters into the attic space, the insulation is not an air barrier. It's going to bleed through and accumulate on the cold surfaces, in this case, the sheathing plane, which is pointed at the night sky and is extremely cold and overnight. So this is where we get excessive mold growth within attic space. This is the critical function of ensuring that if I'm going to do an attic top up, I'm going to address air sealing first. Professional window replacement. So just the examples again of as I was a remediation contractor for 30 years prior to coming on with the engineering and building science, and now as an EA, and so I've installed thousands of windows, and I've done it 100 different ways over our history of building science. And when I go and look at a building today and see the workmanship considerations, it's quite disheartening. And so it's critical for me to impart that there is an easy, simple process for installing windows that gives me an opportunity for future development. It meets the critical needs for today's installation process. There are guardrails in place to ensure that the homes are safe in that critical house of the system assessment. We can see here on the left in this photo that there is no intimacy between the control layers. They're not in contact with the interior control layers. They're just loosely applied. Lots of opportunity for blow-by with air pressure differential in this assembly. Another case where the homeowner reported icing on his windows right away within the first couple, the first winter season. Again, we can see the lack of intimacy. There's really no format here as to what they were trying to do with the components and utilizing those materials effectively. So every manufacturer has their requirements for proper installation procedures. We have our tested, vetted assemblies, and this is definitely not one of them. It's just a waste of material at this point. And another critical component is on the exterior when doing window retrofit upgrades. In this case, and it's difficult to see in this photo, when they trimmed out for the new windows and cut all the vinyl siding back to accept the new components, they cut right through the water resistive barrier in this case. Every single window cut right through the water resistive barrier. So depending on your demographics, your climate zone, in this case, it was an environment with very high driving rain and wind potential, a DWRI index. And so all climate zones have a DRWI index. In this case, it's a very high. It's part of doing a window retrofit. There's actually some guidelines and a checklist in order to do effective window retrofits on existing homes. And in that checklist, it asks, what is your exposure rating for your DRWI? And in this case, clearly none of that was ascertained. And they went in and cut directly through the siding, directly through the water resistant barrier. So any driving wind or rain coming in from the one side, the opposite from trim side, doesn't get picked up by any of the drain planes or any of the effective critical barriers within the water resistant barrier within the wall. It simply bypasses the paper directly into the plywood and into the wall assembly. So, critical interventions in this kind of scenario means you're basically pulling all of these windows out again. You can see in the center photo, the spray foam, none of the windows were actually air sealed under depressurization. So again, just a bunch of money wasted. And now we're going to have to backtrack and address this envelope in a more thorough fashion. Last one is just inconsistency with non-compatible, not using the right products for the right applications. Critical. Frustrating. 30 new windows and only 2 counted for the rebate. And I know we're running out of time now, Jenna. So every window must be labeled. So if you go through a process of accessing a rebate program, having an energy advisor come in the renovation upgrade report that you will receive as a result of the evaluation, it clearly highlights the requirements for the window qualifications in order to, one, meet the installed metrics, but also for the documentation process for Enercan requires the labels be attached to the windows. Again, there's quite a bit of dialogue there that explains the process, gives you some alternatives if say the contractor pulled the window stickers off while you were gone. So again, there should be dialogue on your renovation upgrade report that helps you understand the metrics of the windows. The critical one for me is what I'm seeing, and this is not the only case. This one here, this is actually quite common over my last 2 years here in the Kootenays, is that the homeowner leaves it to the contractor to establish whether those products are on the searchable database or not. The contractor does a quick pass through the information, sees that window is on the listed windows, but doesn't scroll all the way to the bottom to show the listing and delisting date. So, I've actually had this, 2 other times in the last month where 30 plus windows were installed, only 1 or 2 meet the metrics for a rebate. So you've missed out on the opportunity simply because they didn't scroll all the way to the bottom or misread the information in regards to, say, the U factor. U factor, from an energy advisor point of view, that U factor, that 1.22 threshold, it must be below 1.22 because that's the only way I can click on the Energuide button or the Energuide button so that you can get access to the rebate. So it must be below the 1.22 U factor. or an energy rating of 34. Did I miss one? No. And then as if you're in the process of getting new windows and writing up a contract with a contractor, CHBA, the Canadian Home Builders Association, has a listing in regards to called getting it writing, which helps with some of the contract dialogue. So it's critical to ensure that writing the contract, your windows meet the requirements of the program. Put it on there, double check that that it's on the contract, that the windows meet the installation requirements of the manufacturer, BCBC, CSA A440, the guardrails that help ensure that we get proper installations. So lessons learned: check building ventilation first, complete the building enclosure using the vapor barrier, careful with all new wall insulation and no vapor barrier, consider average R value return, talk to your EA, and prioritize air tightness in all retrofits, talk to your EA, and double check references for professionals. Again, talk to your EA to help guide you, and refer to window resources. Again, the EA is a resource for that. Safety items, touch on these real quick because we've already touched on them in previous presentations. So obviously asbestos, it's a no-go. It means I'm not doing any blower door testing if there's evidence of vermiculite or asbestos within the envelope. Lead paint, it's not a problem if it's not disturbed. Rodents and insects. Electrical wiring, knob and tube is a no-go. Fungal growth, be conscious of the existing fungal growth and where that falls on as a response to respiratory conditioning or on the mold index scale. Gas safety, we generally, if you have combustion appliances, we'll do a combustion spillage test to determine if I can turn on all of your extraction fans within the building at the same time, including dryer, range fan, bathroom fans, and I can create more than 5 pascals of pressure differential within the space, you're at risk of combustion spillage from those combustion appliances. So that's the metric as an energy advisor. If you have combustion appliances, I'm mandated to do a combustion spillage test before commencing with the depressurization test. And resource, best practice guide for air sealing and insulation retrofits. You can scan the barcode there and go directly to the BC Housing website. And within there, there's also the BC Housing Research Center and the Learning webpage. An absolute wealth of resources, all kinds of fantastic vetted information within there. And that's it for me. Have we got questions, Jenna?
Great, thanks, Jeff. Yeah, folks, go ahead and pop your questions in the chat. I do see a couple coming through. We had another question kind of similar to one before about ensuring that window contractors are installing windows properly. So I know you touched on a couple resources around air sealing and insulation, but if you just had any other thoughts around ensuring quality installation with retrofits.
Yeah, it's actually a really bone of contention for me. It's something I'm very focused on lately is ensuring that we meet those requirements. So as I said, ASTM requirements of the manufacturers, CSA requirements as far as our Canadian standards. It outlined, CSA A440.4.19 highlights all of the considerations for critical barriers, good installation, best practices. If a contractor was simply just to review that, the requirements within those documentations, you will install A+ windows every time. We provide guidance here at the lab for window installation, continuity and making those critical barriers, whether it's a retrofit, new construction. And like I said, the guides, within the guides, there's plenty of referencing.
Great.
Is there more to that question, or I just get lost?
No, I think you've got it there. And then, yeah, thanks, Terry. Just linked to the Home Performance Stakeholder Council there, which is the registered network of contractors who folks are able to access rebates through. And then Natasha had a question in the chat just about workshop or apprentice opportunities. So Natasha, reach out to me and I'll be glad to connect you with Jeff directly because Jeff loves being part of educational opportunities. So I'm sure you can connect on that.
Yeah.
Any other questions for Jeff about kind of the case studies he went through? Mary asks if you have any recommendations for air sealing ceiling tiles.
That's a tough one. If you're referring to like the foam style ceiling tiles, or are they a metal, or because they're just the aesthetic finish generally. So it depends on whether it's a drop ceiling behind those ceiling tiles. It's finding the consistency, the plane of consistency, which is part of the structural elements.
They're wood fiber ceiling
Yeah,
tiles.
the wood fiber tiles. I mean, if they're accessible, if they're visible from the top side, from the attic side, then that would be the best part, the best case scenario. And it could be anything from a flash and fill with a 2-inch lift of spray foam insulation, and then an insulation top up on top of that to get to your R values. It could be utilizing a more detailed work with sealants and actually air sealing from the attic side. And if that is not accessible, or if it's a cathedral, then you're literally trying to air seal. But that would be a combination of sealants through all the joint profiles within that tiled ceiling, and then potentially a latex or a consolidator paint coating over top of all of it.
Great. They're considering adding vapor barrier and drywall from the underside.
You might want to do an investigation what's behind those tiles first before you get too far down that rabbit hole. Being able to determine because if we just simply skin over there, where we may be creating entrapment, you really do need to know what are the components there and whether or not they'll be beneficial to leaving in place. Obviously, being an old wood fiber, it's going to add some R value. But again, it's that perimeter tie-ins as well. So if you're going to install a vapor barrier, it's great that vapor barrier is there, but you're also going to want to air seal it across that plane as well. So all your ceiling penetrations, whether that's utilizing gaskets, pans, or sealants to create that continuity through those components.
Where's the thermal?
What would be above in the attic still.
Great. Any other questions for Jeff on building science fundamentals or the case studies? All right, Chris has one here. He says, per your comment, adding insulation to the inside or filling empty stud cavities in old homes reduces drying to the exterior. How do you suggest addressing exterior walls in very old houses?
I would, I'm a big fan of just put a sweater windbreaker on it. So if I have a deficient, you're dealing with a number of considerations with interior, trying to address the interior thermal plane. I have intermediate walls. I have all kinds of, electrical components, plumbing, potentially HVAC within those wall cavities. It's a bit of a dog's breakfast. If I want to be really effective about it, I can simply just put a sweater and windbreaker on the outside. And I would eliminate the consideration for all of those interchanges and intersections and complexity on the interior planes, because I generally have fairly straight, clear walls on the outside. And so an effective upgrade would be an exterior air barrier and insulation.
Great, thank you. Are there any like housing types or materials that you cannot add exterior insulation to? Like any examples of homes that wouldn't be the go-to solution?
No, if we look at the physics, from a physics standpoint, all buildings require sweater and windbreaker. That's the truth. If we want to mitigate climate change impacts, or the cost to condition our homes, sweater and windbreakers is really the ultimate answer. There are considerations. So, in the case of if you do have an existing interior air barrier that is effective, then putting in a second air barrier on the outside, the more air barrier, the better. But if that's a critical function on the inside, and I utilize say, a rigid insulation that's not vapor permeable on the outside, I could be trapping components within the wall. So the components used and the science applied to the wall assembly, for me, it's vapor open everywhere, so that I don't have an opportunity to trap moisture. I'm going to reduce risk at every intervention possible. So I'm going to vapor open air barrier components, vapor open insulation, make sure I have drying mechanisms, taking all of the building science, risk mitigation considerations into effect.
Great, thanks. How about in historic homes with rubble foundations? What's the best practice for insulation or waterproofing?
Yeah, unfortunately, I mean, free draining gravel on the outside is your first most critical intervention, ensuring that you have a free draining, access to your perimeter drainage. So we want to keep the water out. So the first intervention is on the exterior, on the positive side, digging out the footings, ensuring that I have drainage, ensuring that I have airflow and free draining ability against the surface of the footing, and making sure that the water is directed away from the building. And then obviously on the inside, to increase thermal insulation value, I need intimacy with that surface, that interior irregular surface. So I'm going to potentially do a spray foam lift to create that continuity through the elements, and then I can back that up with batt insulation or other components to increase that R value. But I'm going to have to rely on spray foam for the intimacy on that irregular surface, because if I was to apply a batt material or a rigid material over it, I create pockets and voids, which will be condensing areas, and I'll get that moisty basement smell.
Great, thanks. And then a similar question about concrete foundation walls in the basement. So this is a 1966 house. If that concrete's currently shedding water vapor to the interior during spring melt, is it better to maintain the ability for that water vapor to escape to the inside, or better to seal it all up?
You're going down a time sensitive slope. So that's a condition that's not going to get better over time. So it's only going to get worse. The ingress will only continue to get worse over time. So any air sealing and insulation in crawl spaces or basements, address the ingress first. You cannot if you've got excessive efflorescence or the white powder forming on the concrete, or you can see cracks or moisture buildup or wet spots, you're going to want to address again, from the positive side, your perimeter drainage, ensuring that the water is getting away, that I have a stop on the positive side of the wall to ensure that water can't get through that wall. And then once I've mitigated any ingress of moisture or water through that, then I can address the interior control layers.
Great, thank you. Any other questions for Jeff? And thanks, folks. I did slip that. I started that poll while Jeff was answering. I know most of you have been on these webinars with us before, but for those of you who haven't, we do take these poll results into consideration when we're planning out future webinars and workshops. So thank you for taking a couple minutes there. Just keep it running in the background. All right. So follow-up question to that, Jeff. So does high humidity in the basement in the summer equal water ingress?
Well, it's either vapor or liquid water, one of the two. So you're either getting vapor accumulation from the horizontal plane coming up through whatever surfaces are at the footing or at the covering the floor. So there's more than likely, especially in a 1960s home, no vapor diffusion within that horizontal plane and the floor of the basement. So you're getting all that moisture from especially in the spring when the melt off is happening, the moisture content, the water table in the ground is quite high. And so you're getting additional moisture into that space, and being a drier environment on the opposite side of that separation line, you're just drawing that moisture in and it's not being regulated out. So there is no interior vapor barrier at this point, or an air barrier within that slab assembly. So you can either address add insulation layers and air and vapor control to that slab layer. Would be the best case scenario is like I say, applying House's system and ensuring that I have those critical barriers to deal with the environmental conditions. And environmental conditions can be on that sixth side of the box, which is the footing or foundation or slab.
Great. Thank you. All right. When encapsulating a crawl space, do you have any key things to address or keep in mind for a successful retrofit?
Air leakage is going to be your most important one with the crawl space, because you've got quite a number, your interior conditioning is causing a load on that footing. So you're drawing air in, or you're drawing temperature in, or pushing temperature out, depending on the seasons. So, ensuring that air sealing in the basement is critical, and that the ventilation ratios are there to maintain the environmental conditions. So we don't want obviously high humidity. We don't want low humidity. We want to be within the zone with the humidity levels and maintain the conditioning. And that ventilation either needs to be, a loop system within the home through an HRV, through your mechanical systems. If you're going to close in the basement, it's going to have some conditioning aspects to it now, which is going to control the ventilation rates and the moisture and humidity levels. But that's, you can't just simply close in a crawl space and not address the airflow or the ventilation rate or the humidity levels. I highly, advise that a cheap on the Amazon interior climatic condition monitor, so you know what your humidity ratio and temperature ratios are in the space. It's a bit of an eye opener in a lot of cases.
Great, thank you. We have a few more minutes, folks, if there's other questions from you on the call. I think I went back and addressed all the questions that were in the chat, but if I missed you, just put it back in there. We'll just give it another minute or so and see if anything comes through. Really working on getting that Jeopardy music to play in these moments. Thanks, Mel. All right, well, if nothing's coming through, okay. I knew as soon as I said that a question would come through. All right, Tom asks, sealing electrical boxes. Can a sealant be used on the interior side to improve the air sealing?
There really is no rules of what you can or cannot do when it comes to air sealing. But if you're doing sealing electrical boxes or any electrical boxes, I prefer to use the intumescent putty. It'll be a red brick or sheet putty in the electrical aisle. You can also utilize the gray material. So I'm going to zoom in here. So here would be a sealing penetration. And if you can, did I lean against something? It just changed camera. Oh, you did that. Okay. So I don't know how clear that is, but, and it's backwards to me. It's like trying to cut your hair in the mirror. So that is the intumescent putty. And so I've just made a couple little little blobs and covered up the extra holes within the box. And then take a worm and wrap it around where the wires come into the box. So the box itself, as long as there's no gap seams or penetrations, can be air sealed. Here's a switch plate. So this is highly effective. Now, I've had some really keeners go around. So in the best case scenario for me was a custom home in Castlegar, 2004-ish home. It has all the critical barriers, just not well executed. And so being a custom home, he had excessive amounts of switches, plugs, and penetrations. He went around with the intumescent putty, sealed all of those components up, and reduced his air change metric by just shy of 2 air changes on quite a large home. So it's based on volume metric. So that's quite a bit of improvement just by diligent air. And then the last step in that is air sealing the box to the surrounding finishes. So if I'm in an airtight drywall approach, or that is the majority continuity within my envelope, what I'm doing is transitioning from that drywall finish to the box, air sealing the box itself, transferring back out to the remaining wall, and carry on. So I want all of these components. So my first step is to turn off the breaker, pull the components out, air seal the interior of the box with the putty, and then air seal the box to the drywall itself. The gaskets aren't going to solve that for you because the air leakage is actually in the middle. But if I create that continuity through the components, I now have what would be termed as the airtight drywall approach.
And then what would be the right product for the gap between the drywall and the box?
Well, I'm going to want to use a high homogeneous product. I'm going to, not generally something off of the shelf at the home hardware, but everything from Alex Plus to a polyurethane, just no silicones. You're not going to bond to any of the drywall finishes or anything like that.
I'll throw a little tip in for fun. The cut edge of the drywall is powdery, and you can use what's called a dust proofing. Mix Wellbond, white glue and water 5:1 and paint it. It'll become crunchy, and then you can do your seal.
Perfect. Thanks, James. All right, we do have a couple of other questions in the chat, so that should bring us to the end here. So what's your take on having a wood framed wall inside the concrete foundation wall filled with bat insulation when the concrete wall has a peel and stick membrane on it?
On the inside, they have a peel and stick membrane on the inside of the concrete wall, or on the outside?
Aaron, would you like to shed some light there? Peel and stick outside.
Okay, yeah, no, that's fine, because that's your exterior water resistive. That's your protection from moisture in the water table. That's fine. The concrete itself, as long as it's free of cracks or major deficiency, is an air barrier in itself. So you have your air barrier metric. You need to create the continuity through that. If you're going to insulate and build a stud wall on the inside of the basement, you still need the critical control layers on the inside. That peel and stick on the outside is not part of the 5 critical barriers to make up that wall assembly, in the sense that it is only applied to the concrete. It's not attached to your framed wall, right? So you're not creating an air seal on the exterior. You're only consolidating the concrete itself, and add, that peel and stick on the outside is a protection course for the water table. It's not to do with air, vapor, or thermal in that sense. So building the wall on the inside still requires the air sealing to avoid convective looping and air penetration of the wall, right? It's the footing area above the frost line that is critical. So everything below the frost line is a steady 4 degrees year round, winter, summer, fall, doesn't matter. Everything above the frost line to the top of the footing wall is susceptible to the exterior environmental conditions. And that's where you get the cold condensing in the summertime or in the wintertime, because that is the coldest portion of your basement footing. So you want to still ensure that I have all of the control layers on the inside. If I had an exterior air barrier already applied, then tying in that membrane to my exterior air barrier would complete the continuity on the exterior. But in your existing stock home, it's more than likely, interior control layers, and you would still need your air and vapor in that wall assembly framed on the inside of the building.
Great, thank you. And then just our last question here, any preferred materials for an air barrier from the outside over brick? So Casper's thinking of brick and block homes in his area, which often have strapping and early drywall plaster on the inside.
I would imagine they're multi-wise, or are they veneer? If they're veneer walls, I mean, if it's an actual brick wall with multi-wise, which is thicknesses of brick assembly, that's a whole different ballgame than just a fascia brick. I do not suggest going over top of a fascia brick at any rate.
Brick is tied into the block wall.
Oh, brick over block. Wow. Yeah. You're looking at more European standards where they basically insulate between the two walls to create that continuity, and then you can apply whatever layers to the outside. That's a bit of a unique scenario. I don't think we could answer that in one go here. If you want to consult further on that one, I can go a deep dive with you and utilize some, James and the other resources, but that's not something that I would necessarily. There is actually a range, and if you look at the European standard, especially in England, where this is more common, this type of construction assembly, they've got all kinds of solutions and exterior insulation, plastering. There's a whole range in the European market. So, and we're quite keen on what those impacts are in the few scenarios where we have that locally. So if you want to get more onto that, we'd have to take a deeper dive than what's available here today.
Great, thanks, Jeff. All right, so that brings us to the close, folks. We do have a third part in this webinar series where we're going to bring together kind of everything covered in part 1 with the building science fundamentals, these case studies and lessons learned, and bring it all together for you in part 3. So watch out for the follow-up email that will include the slides and link to today's recording, where we'll have the registration link for that webinar too. Thanks everyone for joining us. Thanks Jeff and James in the background there for imparting some of your knowledge and wisdom. It's great to have you here. We really appreciate it. And I hope everyone enjoys the rest of their day.
Thank you, everybody.